Hey guys, welcome back. I'm gonna make a quick video on proofs, which is associated with double angle identities. I've made a couple of videos previously which were not correlated to double angle, but were still proofs. So you'll notice how this one's slightly different from the previous ones. All right, here I begin. If you look at my first example here, it says establish the following identity. That's my left-hand side and that's the right-hand side. Notice how right-hand side has a double angle associated with it, so please identify that first. If I start, obviously the left-hand side is much complicated looking than the right-hand side, so I'm going to go ahead and get started with the left-hand side. The idea here is to be able to work on left-hand side, and at the end, keep in mind how cosine theta, 2 theta, has 3 formulas. So somewhere around here, when it starts looking like one of the 3 formulas, we know we have reached our destination, because it's not going to be directly cosine 2 theta. As you work on left-hand side, it's going to start looking like one of the formulas for cosine 2 theta. So that's what we're looking for. All right, so when I start with this, it would be nice to convert cosine squared theta into sine squared theta using the Pythagorean identity and see if that helps us. Once I convert cosine, then the next thing I want to do is go ahead and distribute this so we are getting rid of all the parentheses. So multiply there, and then plus 2, and then I have sine squared theta times sine squared theta. That makes it sine to the 4th theta. And it just happens so that the very next term is the exact opposite of 2 sine to the 4th theta minus 2 sine to the 4th theta. That disappears. So I'm left with 1 minus 2 sine squared theta. And then, as I said, keep an eye for one of the formulas for cosine 2 theta. And this is a formula for cosine 2 theta. I think it's the third one. And hence we have proved it. Moving on to the second one. This one says go ahead and prove sine to the 4th theta minus cosine to the 4th theta is equal to negative of cosine 2 theta. So keep that negative in mind. There's a negative on the outside. Now when I look at this identity, it feels very similar to difference of squares. What was difference of squares on the side? I'll write that down again. A squared minus b squared. If I identify difference of squares, then I can go ahead and factor it as a minus ba plus b. Although this is to the 4th power, the 4th power is basically square of the 2nd power. So this can be written as square of sine squared and cosine squared, which makes my a and b value that this is the a value. A value would be sine squared theta, and b value would be cosine squared theta. So if I do a minus b, a plus b as factoring it out, that won't fit in there, would be sine squared theta, so a minus b times a plus b. And once I do that, this right here is our Pythagorean identity. The value for that is 1, and we're multiplying by 1, which I can completely erase, because multiplying by 1 is the same thing. But just know that that's the Pythagorean identity. And once I get this part here, once I get this part here, this is very similar to cosine 2 theta formula. One of the formulas for cosine 2 theta is cosine squared theta minus sine squared theta. So it's pretty much the same, except the signs are swapped. So I can totally pull out the negative and swap their signs. And if you notice, when I redistribute, I get the original one back. And hence, now I have a negative on the outside, and this is the formula to cosine 2 theta. And I have proved the identity. I have 4 total examples. Here's the third one. Prove that this is equal to also cosine 2 theta. So keep in mind, this is second double identity, so one of the formulas should start popping up at some point in time. When I look at the secant squared, I feel like converting it to its reciprocal identity. And then also, sine squared theta is the Pythagorean identity equivalent to cosine squared theta. Okay, so I've used both Pythagorean and reciprocal identity in this step. Now, from here onwards, it seems tempting to be able to cancel those two, but you cannot, because this term is together and is connected. The 2 and the cosine squared are connected to each other with a minus sign, so I can't do that yet. However, if you distribute, we end up with 2 cosine squared theta minus 1 over cosine squared theta times the cosine squared theta. And now you can totally go ahead and cancel these. That leaves us with 2 cosine squared theta minus 1, and that is one of the formulas for cosine 2 theta. And we have proved that identity as well. And the last one here says prove that sine 2 theta is equal to all that stuff. So this is the sine 2 theta. Please identify, again, a double identity, but for the sine formula. That's not double, that's not double, that's not double. Okay, having identified that, also the formula to this is 2 sine theta cosine theta. So when I'm solving this, I'm looking forward to running into this. And once I run into that, then I know I've proved it. All right. When I look at this right-hand side, I do see 2 as the GCF, and then I also see tangent theta as the GCF. Once that's factored out, we are left with, not the 2, because 2 is gone, minus sine squared theta. All right, at this point, I can go ahead and convert tangent to its quotient identity, and then 1 minus sine squared can be written as its reciprocal identity, not reciprocal, Pythagorean identity as cosine squared theta. Once I do that, I can totally go ahead and cross one of the cosines with the cosine. That leaves me with 2 sine theta times cosine theta, and that, like I said, is what we were looking forward to get to. So here was a quick video on proofs that require double angle, and my next video is going to be on half angle identities. Alrighty, see ya then. Bye.